Hi guys, today we want to talk about curvature of a smooth curve. So let's define smooth, what that means. So a parameterization R of t, so if we have some vector valued function R of t, is called smooth on a given interval if the derivative of that function R of t is continuous and if it's not equal to the zero vector. So if C is a smooth curve, defined by that vector value function r, then we define the unit tangent vector, and we looked at this last time. We define the unit tangent vector to be capital T, and we'll call that the vector T. So I'm just going to do that vector a little bit thicker. So T of T equals the derivative of R of t divided by the magnitude of the derivative of R of t. And we looked at that last time. Okay, and it indicates the direction of the curve, right? So that's what that tangent normal does. It shows us which direction the curve is going, and it's a unit vector. So its magnitude is 1. So you'll notice in the figure below that that curve, the unit tangent vectors, change direction pretty slowly when the curve is kind of straight. So when we have a more straight curve, they're not changing as rapidly. Whereas when the curve is more steep or bends more sharply, we've got a pretty sharp direction that's happening there. That characteristic of a curve is called curvature. Okay, so curvature of C at any given point, it measures how quickly the curve changes direction at that point. So if we define it to be the magnitude of the rate of change of the unit tangent vector with respect to arc length, then what we would see is that the curvature, and curvature is represented by a kappa, and a kappa is usually kind of this funky K, like in text it has like a kind of a loop like that, and it's really squatty type K, but it's kappa, it's a Greek kappa. And so kappa would equal the magnitude of the derivative of the t, the unit tangent vector, with respect to the arc length. Okay, well, that's great, except that we know that reparameterizing a curve with respect to arc length can get a little bit messy and maybe is not the best thing to use. So let's think about a way that we could rewrite the curvature formula just a little bit. So keep in mind, we know that dt ds, let's go back to the pencil. dt ds might look like this. So if we have this with the derivative of that unit tangent vector with respect to x, this probably came about because we did the derivative of that unit tangent vector with respect to time, okay, multiplied by the derivative of time with respect to the arc length. Well, really that came from the derivative of the unit tangent vector with respect to time divided by the derivative of the arc length with respect to time, and that's how we reparameterize this. Well, let's go back to what we did the other day when we talked about the arc length function, and we looked at the arc length ds dt. We said ds dt is equal to the magnitude of each of the components of the curve of r. So we said it was the magnitude of r. Sorry, the magnitude of r prime of t. So let's rewrite this. Let's take this dt dt and let's put that just in the notation that we used previously, and let's call that t prime of t over r prime of t, and we're going to be taking the magnitude of that. So this kappa, this curvature, can equal, or another way that we can rewrite that curvature formula is the magnitude of the unit tangent vector divided by the magnitude of r prime of t. So let's look at an example. Let's show that the curvature of a circle of a radius a is 1 over a. So I'm going to write the two curvature formulas that we just looked at. So we have kappa equals the magnitude of dt over ds. So this would be the derivative of the unit tangent vector with respect to the arc length. Or that's equal to the magnitude of the derivative of the unit tangent vector over r prime of t. Same thing. Okay. Now, if we're going to have a circle with a radius a, I don't know how many of you remember looking at the circles. When we look at a circle in a vector function, if you recall, that formula is a cosine, well, a because the radius is a, sorry, a cosine of t, comma, a sine of t. So if we go through this formula, we might want to find the derivative of this first, and that would give us negative a sine of t and a cosine of t. And then if I do the magnitude of that, because I'm going to need that for my formula, we're going to get the square root of, let's see, a squared sine squared t plus a squared cosine squared t, which equals the square root of, let's pull out that a squared, and we get sine squared t plus cosine squared t, which is just 1. So really we get the square root of a squared, which is just a. So my derivative of that vector is a, or the magnitude of the derivative of the vector is a. So now let's look at the unit tangent vector. Well, remember the unit tangent vector, if we're going to do this, is the r prime of t. So we get negative a sine of t, a cosine t, we already found that piece, over the magnitude of r prime of t, which is just a, we found above. So really, when we rewrite this, we get the vector negative sine t cosine t. Okay, so there's my unit tangent vector. Well, the formula that we need for kappa, we need the derivative of the unit tangent vector. And the derivative of this, let's look at that. D prime of t would be, the derivative of negative sine would be negative cosine of t. The derivative of cosine would be negative sine of t. Okay, so we would have the magnitude of this over, well, we already found the magnitude of r prime, but let's just rewrite it anyway. Okay, so we have the magnitude of this. So we'd have the square root of cosine squared t plus sine squared t over a. So we get the square root of 1, which is 1, over a. So we have just shown that my curvature for the circle with a radius of a is 1 over a. Okay, well, there is also another formula that we might use for curvature that takes our number up to 3. That is oftentimes easier to apply. So this particular formula for curvature can be easier to apply. We'll look at an example of why it's easier to apply. And that is that kappa. See, that kappa is a little bit weird. And it's always a little bit different. There's a different font I used where it looks a little bit different. Has more of a curve at the K. But anyway, we have the magnitude of r prime of t crossed with the magnitude of the r double prime of t over the magnitude of r prime of t cubed. Okay, so let's look at an example. Remember we looked in class at that twisted cubic function, which was kind of cool to look at. So let's look at finding the curvature of a twisted cubic function. Okay, so we know we have the two possible formulas, so I'm just going to rewrite those here and then we'll begin. Okay, so we're going to start with that first formula. We're going to attempt to find the unit tangent vector and then take the derivative of that. And if we go and find the unit tangent vector, first thing we need is r prime. So r prime of t would be derivative of each of those components. We would have 1, 2t, and 3t squared. And then if I find the magnitude of that, so the magnitude of this r prime of t equals the square root of 1 squared plus 2 squared, or sorry, 2t squared plus 3t squared squared. 3t squared squared. And so let's simplify that, and we get the square root of 1 plus 4t squared plus 9t to the fourth. So now we want to find the unit tangent vector. And remember, the unit tangent vector, that t of t, is equal to the r prime of t divided by the magnitude of r prime of t. So we would get 1 over the square root of 1 plus 4t squared plus 9t to the fourth, comma, 2t. Is anybody else seeing a problem with all of this? Because in order to keep going with this, I now need to take the derivative of this. Yuck. I don't want to try to take the derivative of this, because think about what the derivative of that would be. This first one, we would have negative 1/2 times 1 plus 4t squared plus 9t to the fourth to the negative 3/2 times the derivative of that inside piece, which would be 8t plus 36t to the that's just the first component. I don't want to do that, okay? This is where using that other formula is going to come in handy. So let's see what that might look like. Well, we've already taken the first derivative, okay? So let's just remind ourselves that that first derivative is right here. We're going to pull that down. We're going to use that. And so let's take the second derivative now. So let's take the second derivative. I'm going to just write no. Use other formula. Okay, so let's take the second derivative. R double prime of t equals, so we get 0 to 6t. So I need to do r prime cross with r double prime for the other formula. And if I do that cross product, remember that's the matrix. And when we set up the matrix, we would have I, j, k. We have 1, 2t, 3t squared, and 0, 2, and 6t. And remember that the signs for these go positive, negative, positive, just so we don't forget. Okay, so the cross product of this, for the I component, we'd have 2t times 6t, so 2t times 6t minus 2 times 3t squared. So 12t squared minus 6t squared. So my first component would be 6t squared minus, because it's negative j, and then we're going to do 1 times 6t minus 0. That's great. So minus 6t. And then the k component of this is going to be 1 times 2 minus 0. So I like that. That makes it easy. So 1 times 2, we get 2. So there's r prime cross r double prime. And then I need the magnitude of that. So the magnitude of r prime cross r double prime is going to be the square root of 36t to the fourth plus 36t squared plus 4. And so then my curvature is going to be the square root of that, 36t to the fourth plus 36 t squared plus 4 over the magnitude of, the magnitude of r prime cubed. So let's do the magnitude of that. The magnitude of this, not pretty either. 1 plus 4t squared plus 9t to the 4th to the 3rd. And then I need that is the magnitude, sorry. Now, this is great. So this is my curvature, but the part that we haven't dealt with just yet, the part that's going to make it a little bit easier, is that it says at the point 0, 0, 0. Well, the problem is that's x, y, and z. I don't have an x, y, and z in this curvature problem, but I do have a t. Can I figure out my t value based on the point? Yeah, we know that the t value here would have to be 0 based on the curve that was given. So I'm going to evaluate this whole thing when t equals 0. So that makes my life really easy when t equals 0, because the curvature here is going to be the square root of 4 over this 1 to the 3rd power. And so we get 2 over 1. So my curvature for the twisted cubic at the point 0, 0, 0 is 2. Okay, well, there's yet one more formula that we're going to look at it, and it's in a special case. It's the case when a plane curve has an equation y equals f of x, so a function with respect to x, and therefore x would be our parameter. And so what we're going to do is we are going to write, oops, I see I forgot my notation. R of x would be x comma f of x. Okay, well, I'm going to take this to the 3rd dimension since all of our other curves so far have been in 3 dimensions. And we would write r of x, the vector valued function r of x is going to equal x, f of x, 0. Okay, so let's go through and let's derive what this other formula could be if our equation is relating y equals f of x and x is our parameter. So our r prime, I'm going to ignore the vector symbol, just understand it's a vector. R prime of x equals 1 f prime of x, 0. And r double prime of x equals 0 f double prime of x, 0. So now we need the cross product of this. So if I do r prime cross r double prime, we would get I, j, k, 1, f prime of x, 0, 0, f double prime of x, 0. Okay, so we would get 0, zeros is the first one. On the next one, j minus, it'd be the negative, we'd get 0, 0 also, so that's fine. And then on k, we'd get 1 f double prime of x minus 0, so this would be f double prime of x. And I also need the magnitude. So if we look at this formula, where we have r prime t cross r double prime of t, do you agree that if I take the magnitude, this will just be the magnitude of f double prime of x? Because that's what my r prime cross r double prime is. And then if we look at r prime of t, the magnitude of r prime of t, well, I didn't look at that one just yet. Let's do that. Let's find the magnitude of r prime of t. This is an x, sorry. I think I said t twice, actually. This will be the square root of 1 squared, which is just 1, plus f prime of x squared. So I can rewrite my curvature function in terms of x's to be 1 plus f prime of x squared, the square root of 1 plus the f prime of x squared cubed. Okay, so this would just be another way to look at it. So I wrote that down right here. We can simplify that square root of and make it 1 plus f prime of x squared raised to the 3/2. You could do square root also, but let's look at an example that deals with this. Okay, let's find the curvature of the parabola, which we know what that looks like. Y equals x squared at the points 0, 0, 1, 1, and 2, 4. So let's look at our different curvature values. So first thing we want to do, if we're going to use the new formula that we have, is knowing that our function is f of x equals x squared, which means then when we take the derivative, we get 2x, and the second derivative is 2. Okay, so my first part of my formula, my curvature, we'll get to that. We need also, 1 plus, we're good. Well, actually, we have everything. We've got everything we need. All right, so let's do our curvature formula. So curvature would be the magnitude of the second derivative. Well, the magnitude of the second derivative is just 2, divided by the square root of 1 plus 4x squared to the third power, or we can write it as 1 plus the first derivative squared, so that'd be 4x squared to the 3/2 power. That's using my curvature formula. And if we go through and do k of 0, we would get, plugging that in, we'd get 2 over 1, which would be just 2. So the curvature at 0, 0 is 2. The curvature when x is 1 would be 2 over, that would be 1 squared is 1, so 5 to the 3/2 power. And the curvature at 2 would be 2 over 17 to the 3/2 power. Okay, so let's look at what that looks like in relationship to a graph of the curvature. So you can see below that we have a picture of y equals x squared. We know what that looks like. And when we go and plot the curvature function, if y equals the curvature function, at 0 it'd be 2. At 1, it'd be 2 over 5 to the 3/2 power. Okay, so we're getting the number's becoming smaller. And then 2 over 17 to the 3/2 power is even closer to 0. So that's what it looks like on a picture. Now, I want to go back because we could redo this same problem, and I just want to look at it a different way. I want to look at it in terms of the other formula that we had. So we could rewrite y equals f of x as a vector valued function, r of t, in terms of t, and the parameter t, we would just replace t with x, would be t squared 0. This vector valued function would be the same curve as f of x equals x squared. And if we went through and did the math here, r prime of t would be 1, 2t, 0. We need the magnitude of r prime of t, and that would give me 1 plus 4t squared, the square root of that. We would need r double prime of t, which would be 0 to 0. And if we do the cross product of r prime t cross r double prime of t, we get the vector 0, 0, 2. You can do that on your own if you want to check it. But look at this. You guys, the curvature is still the same. So if we look at the curvature, that formula, remember, is, I'm just going to write it up here, r prime of t cross r double prime of t, and the magnitude of all of that, over the magnitude of r prime of t to the third. So on our problem, we would have the square root of the cross product, which would be 2 squared, which would be 4. So square root of 4 over the square root of 1 plus 4t squared to the third. Simplifying, we get the same thing we got before. 1 plus 4t squared to the 3/2. So you can see the formula for the curvature is the same, regardless if I'm doing it in terms of x or in terms of t. So there is curvature for you. All right, We will see you soon.